Okay, we're recording. Does it tell y'all that we're recording and ask you if you want to leave?
It does.
Yes.
That's funny. Okay, groovy. So here we go. Okay. So we went through definitions of things last time, and we'll just come back to this page if we need to review it. I think we just barely flew through these. So all of the reciprocal identities, we talk about them constantly, so should be nothing new. We have two ways to write tangent and cotangent. We can write them as reciprocals or as quotients of sine and cosine. We have the Pythagorean theorem. The three Pythagorean identities. The one you want to remember is cosine squared is 1. The others can be brought very quickly from that one. If you remember two of them, remember the tangent plus 1 is secant, and sine squared, cosine squared is 1. And then the quadrants where all of the trig functions are positive. So sine and cosecant in first and second, cosine and secant in first and fourth, tangent and cotangent first and third. You notice that every one is positive in two quadrants. So everyone is negative in two quadrants. Ben, I'm going to give you power. Is that okay?
Yeah, that's fine.
Oh, hi, Lynette. Okay, great. So we've got all of these identities. And the one that we're going to look at first is the period. So I'm going to tell you that the sine of 49 pi over 12 and the sine of pi over 12 are the same. And you're going to tell me why. Why are those the same? Why is the sine of pi over 12 the same as the sine of 49 pi over 12?
It's because there's a 12 in the denominator.
So that's the thing that has to be there in order for this thing to work, this identity that I haven't mentioned yet. I have mentioned it, but we haven't identified it here yet. But yes, the 12 has to be the same, because you notice that both fractions are not, you can't reduce them anymore. So yes, the 12 is the same. What else? I'll give you a hint. What do you have to subtract from 49 pi over 12 to get to pi over 12?
$48.
Yes. 9 pi over 12, and we're subtracting 48 pi over 12. Can we reduce the fraction 48 pi over 12?
It would just be yeah,
4.
Yeah. So we've got 49 pi over 12 minus 4 pi equals pi over 12. Oh, thanks, Ben.
No problem.
But why is the sine and tangent and cosine everything for 49 pi over 12 the same as all of the trig functions for pi over 12? Why is subtracting 4 pi gonna give us the same sign?
Because they're the same angle.
That's right, because they're in the same position, right? So here's pi over 12. And I just know where it is because pi over 6 is twice it. So we've got pi over 12 and 49 pi over 12. Well, we subtract 4 pi to get to pi over 12. That means that we're basically in exactly the same position. So what properties that we looked at, I think they're on this page. Yes. What property from this page says the thing that we know to be true?
Could you say that one more time?
Which property on this page, so we're looking at all of them, says that if you go 2 pi around in any direction, you're going to end up with the same trig functions?
Periods and symmetries of trigonomic functions.
That's right. That's exactly right. So we've got, here's the sine. The period of sine is 2 pi, and that means we can add or subtract 2 pi, 4 pi, as many pi's as we want, as long as it's even, and we get to the same value. So that's why the sine of 49 pi over 12 and the sine of pi over 12 are the same because of the periodic property of sine. So just tell me, is the cosine of 25 pi over 12 going to be the same as cosine of pi over 12? And if so, just tell me why.
Yes, because we can subtract 24, which is equal to 2 pi.
Very good. Very good. So let's, oh yeah, okay. So let's look at, to me, these are harder with degrees. But let's just briefly look at, we're starting at the cosine of 75. So that's 15 degrees away from 90. This is 90 degrees, 7, 5 degrees. Let me see what it is. How can we prove that the cosine of 436 and the cosine of 5 are going to be the same? I think this should be a 5.
We can add or subtract 360 degrees.
Very good. So we've got 35 minus 360. I love it when we get to borrow. 13 minus 6 is 7. That was, when I was a kid, that was my favorite subtraction to do, 13 minus 6. Isn't that dumb, bizarre? Anyway, okay, so we started at 430, ended up at 75 by subtracting one full rotation, 360. So whatever value you have for one has to be the same as the value for the other. And what do you think you'll subtract from 795 to show that these values are?
Would it be two full
360
rotations?
twice.
That's right. That's right. So let's just do the math really quickly. 360 times 2 is 720. And if we start at 795, oh, we don't get to borrow. And subtract off 720, we do empty at 70. Okay. Tangent and cotangent are more fun because their period is pi, which means you can add pi, you can add 2 pi, you can add 10 pi or 11 pi. And the tangent and cotangent are the same. But this time we also have a negative inside, and the negative comes back to even and odd. We know that the tangent is odd, and that means a negative inside becomes a negative outside. So let's see. We've got 4 tangent of negative 3 theta. And what can I do with the negative?
Put it on the outside.
And this is because tangent is odd. And now let's look at the second part. We have negative 5 tangent of 3 theta plus pi. And what is this the same as? Good, thank you. So this equals negative 5 tangent of 3 theta based on the periodicity of the tangent. And now we've got that 4 tangent of negative 3 theta minus 5 tangent of 3 theta plus pi is equal to, well, the first one holds a negative 4 tangent of 3 theta. The second one drops the pi, minus 5 tangent of 3 theta. And I know it's a weird looking term, but do you see that whatever it is, the tangent of 3 theta is common here?
Yes.
So if we have -4 of them in the first term and -5 of them in the second, how many do we have total?
-9.
So we can't get rid of the theta, the 3 theta, or the number in front, but we can take two things that look pretty wild and combine them into something that looks less wild. When that
Uh,
wonder what. Yes,
So is there one of the rules? So you know the rule that we can, if the negative's on the inside, we can put it on the outside. Is
Yeah.
there a rule for the pi? Just dropping it?
yeah, right here.
Okay, cool. Thank you.
So, and that's also the same for cotangent. Okay, let's do one other fun thing, and this one I am going to let y'all do try this. But let's take this sine x, secant squared x minus sine x, all divided by sine x, secant plus sine x, and let's make this not a fraction and as simple as possible. And usually as simple as possible means one trig function rather than, I think we've got two going on. So what do you want to do to start to simplify this?
Multiply by the denominator.
So multiply what by the denominator?
The whole thing.
We could, but but since the denominator multiplying by the denominator isn't going to, it'll just make the numerator bigger and it won't change the denominator. So
Oh,
Can we
right,
cancel anything out?
say it again.
Can we cancel anything out?
We can factor and then cancel. So what do you want to factor?
It looks like we could factor a sin x out.
Be left with secant squared x minus 1. And what about in the denominator? What are we going to be left with?
Secant plus 1.
And now we definitely can strike out the common sign, but I have a fraction in the answer. I've got secant squared. Okay, I've got secant squared minus 1 over secant plus 1. How can I reduce that fraction? Is there a factoring thing that exists in that fraction?
There's a secant squared and a secant.
Okay,
You could factor secant squared to be just secant times secant.
okay. We could write it that way, but I'm going to do something that will make it clearer, maybe. Is this fraction similar to the fraction we had? Is the fraction a squared minus 1 over a plus 1 similar to secant squared x minus 1 over secant x plus 1?
Yes.
Yes.
And is it more obvious how to factor the first fraction, a squared minus 1 over a plus 1?
Yeah.
How?
It would be a plus 1 times a minus 1.
Good. And that's called
The difference of squares.
we're going to use that so much every single day that you'll love it as much as I do by the end. So we can strike out the a plus 1. We'll be left with a minus 1. We can do the same thing here. Secant squared x minus 1 is secant x plus 1. Secant x minus 1, all divided by secant x plus 1. And we can divide out the common factor. We're left with secant x. Cool. So we're going to remember for one thing that this notation is just notation for this secant x squared. We write the square in the middle so that we don't have to use parentheses every time. Because if we didn't use parentheses and we put the square on the outside there, it would mean secant of x squared. We just assume that the square goes with the argument, the thing being plugged in. But this idea going back and forth in your head that secant squared x is secant x all squared, that's really important. Okay, I do want y'all to do this, try this. So I want y'all to simplify so that there's only one trig term and no fractions. And I'll be here, but I'm gonna go away. Yeah, y'all were all saying correct things. I sort of let you go a little bit because that's how you learn this stuff. And we're gonna be stretching our wings. I'll just put it that way. Because the next step is actually proving things. So there's a procedure, and you have to follow this procedure in ALEKS, but actually I'm probably not going to have us do proofs in ALEKS. It's just not a happy experience. So left-hand side, LHS. Right-hand side, do I have it here? RHS. Is that an okay, I don't remember what you call these things. It's not an abbreviation. Anyway, is that okay for you? All right.
It's okay.
Have to start on the left-hand side, and that's kind of a convention in proving trig functions. We want to manipulate only the left-hand side. We cannot go from side to side. We want to manipulate the left side until it looks like the right side, and then we'll be done. And just so that it's easier for us to communicate, we're going to use some kind of column thing. So one column is just going to be the justification for the step. And we're starting with secant squared x, pardon me, secant x minus tangent x all squared. We want to end up with 1 minus sine x divided by 1 plus sine x. And I have this structure more beautiful in the notes. So I'm going to go outside of the structure to make it so I've got enough room. But the page 3 of the notes starts with this proof, and it has all the steps. So let's start. Let's see, we've got secant x minus tangent x all squared. And what trig function is in the goal?
Side.
Fine. Can I write tangent in terms of sines and cosines?
Yes.
Can I write secant in terms of sines and cosines?
Just cosine.
Right. So in fact, what do they both have in their denominator in term if we write them in terms of sines and cosines?
Cosine.
Yeah, so we can add that. So let's do that. We'll have 1 over cosine x minus sine x over cosine x all squared. And when we combine these, we'll have 1 minus sine x divided by cosine x all squared. So far, so groovy.
Yep.
Alrighty. So now let's go ahead and square things. Well, the justification for the first step is reciprocal. Reciprocal and quotient identities. And the second step is just algebra. And squaring everything is just algebra. So I'm going to square the fraction first, and then we'll square the parts. So we have 1 minus sine x all squared, and we have cosine x squared. Let's do the numerator first. How do you square a binomial? So if we have a minus b all squared, how do we square it?
The FOIL method.
You can do FOIL, but I want you to remember how to square. So in general, I think of it as a plus or minus b squared is the first guy squared. The sign is going to be the same in the middle. First times second times 2. And then always plus the second guy squared. We're going to use that so often that if we have to do FOIL every time, it'll get laborious. So let's see. What is a in this scenario? What is a?
1.
1.
1 squared minus 2. And what is b?
Sine x. Negative sine x, I guess.
Yes, exactly. And then negative sine times negative sine is
Positive side.
That's nicer. And the denominator. How do we write cosine x all squared?
Cosine squared x.
And let's think about the goal. Oh, we wanted 1 minus sine x in the numerator. Huh. I wonder if we could go back here. Actually, we did this squaring thing because I want you to practice it. So we have 1 minus sine x times 1 minus sine x, because we have 1 minus sine x squared. And I'm doing this because the goal has one of them in the numerator. In our denominator, we have cosine squared x. Golly, it's too bad we don't know a connection between cosine squared and sine squared. But do we?
Yes.
And what is that connection?
Wasn't it like cosine squared plus sine squared equals 1 or something like that?
And this I want you to know, just period, no. So how can I write cosine squared x in terms of sine x? How can I get the cosine squared x by itself?
Subtract sine squared x.
Okay, good. So we've got cosine squared x is equal to 1 minus sine squared x. So is it fair to replace this cosine squared x with 1 minus sine squared x?
Yes.
I'm going to write this step again. 1 minus sine x times 1 minus sine x divided by cosine squared x. And we changed cosine squared x to 1 minus sine squared x. Let's take a look. Oh, the justification here is Pythagorean identity. And we use the Pythagorean identity because cosine squared x plus sine squared x is 1 is a Pythagorean identity. Let's look at the goal. What do we have in the denominator of the goal?
1 plus sine x.
And we've got what right now in the denominator?
1 minus sine squared x.
Do we know how to factor 1 minus sine squared x?
Yes.
Yes, how?
It would be 1 minus sine x times 1 plus sine x.
Beautiful. And what is that called? That factoring.
I'm not sure.
The difference of two squares. So this is the difference of two squares. Because we have a 1 squared, which is 1 squared, and a sine squared. And what happy thing do we notice now?
We can cancel out one of the 1 minus sine x's.
Excellent. And what are we left with?
1 minus sine x over 1 plus sine x.
Yay, that was the goal. And I want you to notice something. The proof that I wrote up, I squared first. So I had secant squared x minus 2 secant x tangent x plus tangent squared x. And then I put everything in terms of sines and cosines and got to the answer. So there are loads of correct ways to go from A to B. This was a longer way than what we did over here. But they're both okay. I want y'all to start with tangent x plus secant x all squared and end up with 1 plus sine x over 1 minus sine x. And try to do it in 8 minutes. Is that fair?
Yeah, that seems good.
Let's start from the beginning, just to make sure that we're doing algebra and all that. It takes a lot of algebra, but algebra is like love, so it's okay. Sorry. There we go. So did you square the binomial first, Ben?
That's what I did.
Okay,
No, I did not.
what did you do first?
Who are you asking, Ben or me?
Either one of you.
Oh, well, for me, I expanded the square using the a squared plus 2ab plus b squared. Right?
Okay, so that'll give you tangent squared
And square.
plus 2 tangent x secant x plus secant squared x. Is that what you got, Sarah?
Yes, exactly that one.
Is this what
Then
you did something different?
Well, I changed tangent and secant in terms of cosine and sine first.
Okay, that's a great way, and we're going to do it that way in a minute. This way, we just get to practice more algebra. So what can you do at this step if the goal is to get to something that has only signs?
so we can technically. So what I did was I put it into fractions, every single one of them,
Okay,
to see what I can have as compared to cosines and sines. So it's like more of a visual map to see what's going on. So tangent will be sine over cosine, right?
all right.
Plus 2 times, oh, so it'd be sine over cosine, and then as well as, was it 1 over cosine? Yes. 1 over cosine.
With the code. So secant has to go with cosine.
Cosine, right? So it's 1 over cosine plus 1 over cosine squared.
Okay, great. And how many cosines are in every denominator?
There's 2, 5. There's 5 cosines.
Denominator.
Oh shoot.
The first, 2 in the second, 2 in the third.
6.
But we've got 2 in each. So we have a common denominator.
Oh wait, okay, I see. There it is.
Cosine squared x here, cosine squared x, here cosine squared x, here cosine squared x.
They
So,
all share cosine squared x.
yeah. And the numerator is going to be sine squared x plus 2 sine x plus 1. And this is where the pattern of squaring becomes really important. We've got something squared plus 2 times something. That should make us think, is 1 a perfect square?
Yes.
Yes. So if this would work if, because we know sine is squared here. Is the middle term okay? First times second times 2.
So are you saying, is this a perfect square?
Yes, it's a perfect square trinomial. So trinomial 3 terms, perfect square trinomial. So we're going to write it as a binomial squared. And that's algebra. What can we do to rewrite the denominator so that we're closer to the goal?
We also have cosine square x. You could also equal that to 1 minus sine x.
1 minus sine squared x. Yes.
Yes.
This is a Pythagorean identity. And now, why is this almost our goal? Because our goal was to have 1 plus sine x over 1 minus sine x. Why are
Because
we?
there's that. We're off by that square.
How can we?
That sine.
You get a factor.
Yes. And remember, we've got a square here that I didn't write down, but you saw it. Yes,
Oh,
the denominator. So we've got sine plus 1 all squared in the numerator. And how do you factor 1 minus sine squared?
uh,
Was it 1 plus sine x, 1 minus sine x?
Very good. So now, why are we at our goal? It doesn't quite look like our goal. Our goal was 1 plus sine x over 1 minus sine x. And I've got a 1 minus sine x, but I have a 1 plus sine x, and here I've got sine x plus 1, all squared. What can I do?
you can
It would be sin x.
size. Yeah, you could cancel those. Yeah, right there.
Good. And we're left with, and this step is algebra. And we're left with sine x plus 1 divided by 1 minus sine x. Wait, it doesn't look the same. This says 1 plus sine x, and this is sine x plus 1.
Just move the 1 over.
Yes, the sum of 2 things, you can change the order. And I did that mainly to mess with you. Let's look at a skill that you're going to use very, very often. To start with what we were given and go backward. So we're going to start with 1 plus sine x divided by 1 minus sine x. And the goal is to show that that is equal to secant x plus tan x all squared. So we want to go this direction. And the reason why I want to do that with y'all is that it looks like there's nothing that we can do with that first fraction. There's sine is already in terms of sine and cosine. There's nothing I can replace. What do you do if there's nothing obvious to do?
You can solve it the other way and then just reverse it.
How do you mean? Oh, go this way?
Yeah.
Oh, no. I mean, you could, but that would be no fun. So what we're going to do, anytime we have a fraction and it looks like there's just nothing we can do, we're going to multiply by the conjugate of the denominator. What does conjugate mean again? If I have a minus b, what is the conjugate of a minus b?
A plus B.
Very good. Very good. So what is the conjugate of 1 minus sine x?
1 plus sine x.
Beautiful. And as long as I multiply the numerator by the same thing, am I good?
Yep.
Yeah. And you might notice that this is indeed a step that we kind of took before. We struck out a 1 plus sine x over 1 plus sine x. And now we just put them back in. In the numerator, I'll have 1 plus sine x all squared. And in the denominator, I multiplied by the conjugate on purpose, because how many middle terms do we get when we multiply 1 plus sine times 1 minus sine?
Could you say that one more time?
Yeah, so normally when you multiply, let's see, x plus a times x plus b, you'll get, let's see, x squared, ax, bx, ab. So we get an x term in the middle. But do we get a sine term in the middle, or do we only have sine squares? Yes, very good. And that's because it's a conjugate. We've got 1 squared minus, and we've got sine squared. No sine x terms. And the reason that this is good is that it's now looking like something I can replace using a Pythagorean identity. So I've got, let's just look at the denominator. What is the Pythagorean identity that allows me to replace 1 minus sine squared x with something?
Cosine squared.
Yes, exactly. And what is it called, that identity? Starts with a P.
Pythagorean theorem identity.
It's a Pythagorean identity, yes. Beautiful. So now we've got a denominator that has only one term. We've got, we've got 1 plus sine x all squared in the numerator. Can I write, if I've got something squared in the numerator and I've got something squared in a denominator, can I write the fraction as the fraction all squared?
Yeah.
Okay. 1 plus sine x over cosine x, and that's all squared. And we're going to remember that the goal had 1 squared on the outside, but we have 2 terms here in the goal, and we've only got 1 fraction. How can I write 1 plus sine x divided by cosine x as 2 fractions? So this is what I'm talking about. I've got 1 plus sine x over cosine x all squared. How can I write that as 2 fractions?
It would be 1 over cosine plus sine over cosine.
Good. And now do you see that we're there?
Yes.
So the very last step is a trig step. But most of the steps were algebra. So let me see what our, let's see what I skipped. Oh, that's the new material. Moment, por favor. We may do this one of these together next. Which one do y'all want to do together? Sine x, secant x over cosine x, cosecant x equals tangent squared. Oh no, let's try this 7. What do you think?
The one that we just did, the one that we just finished, was that the simplest route to take?
The one that when we went from 1 plus sine x over 1 minus sine x to tangent x plus secant x all squared?
Yes.
Yes,
Okay.
as far as I know.
I trust you.
Thank you. So we are going to prove that 1 plus the tangent squared x divided by x. We will write that as 1 over sine x. Do we have only one Pythagorean identity?
Is that 1 plus cotangent x? Is that cotangent x?
Yes, that's a cotangent. Thanks. Yeah, one of the other Pythagorean identities. Of course, I wrote all over all those pages. One of the other Pythagorean identities is 1 plus cotangent squared theta or x equals cosecant squared. Oh, there it is. And is this, do we have that situation here? Do we have 1 plus?
Yes.
Yes, so we can write that as cosecant squared x, we still have cotangent x in the denominator, and the justification would be a Pythagorean identity. And now we've got cosecant squared x over cotangent x. I don't have any square terms in the goal. What's a good thing to try?
Factoring out the square.
Say it again.
Factoring out the square.
Could factor it out, but we end up going. See, we don't have a square in the denominator to match it. Is there another way to write cosecant?
Could you say that one more time?
Is there another way to write cosecant x?
1 over sine x.
1 over sine x. Okay, let's see. So I could write 1 over sine x all squared divided by, and is there another way to write cotangent x?
1 over tangent x.
There are two ways. So there's 1 over tangent x. Is there a way that,
Cosine over sine.
yeah, cosine x over sine x? The reason that we want the latter version of tangent this time, cotangent, is that we've got a sign in the denominator, in the numerator. We have a sign in the denominator of the denominator. So let's write this without all those parentheses. 1 squared is
1.
and sine squared is
Sine squared x.
and in the denominator we'll have cosine x over sine x. What are the two inside denominators? Because we definitely have a complex fraction here, a fraction inside of a fraction. What is the inside denominator in the numerator?
Sine squared x.
And in the denominator,
Sine x.
what can I multiply? Or, well, if I have a and a squared, what is the least common denominator?
A.
That's the greatest common divisor. That's what they have in common. So the least common denominator is always bigger.
So a squared.
Good. That means I can multiply numerator and denominator by sine squared x. Do you see that we're doing algebra like crazy?
Yes.
Good. So now we've got 1 over sine squared times sine squared. Does anything divide it?
What was that? Sorry.
We've got 1 over sine squared x times sine squared x. Does anything divide out in the numerator?
Yeah, sine squared x.
Good. And what's left in the numerator?
One.
In the denominator, we have cosine x over sine x times sine squared x. Does anything divide out in the denominator?
Sine.
Okay, so what's left in the denominator?
So it would just be 1 over cosine over sine.
You look there.
So, what I want you to trust me on is that these will improve your algebra skills and that you need to improve your algebra skills. Okay. Let's do one more together and then we're gonna go on to another topic. So let's look at oh, here we go. This one's better. Let's look at 1 minus cosine squared x times 1 plus cotangent squared x equals 1. And what do y'all want to try?
So since this is an example, yes.
Say it again. Sorry.
This is an example.
Yes. Example 8.
Does that say cosine?
Since this has 1 minus cosine x squared, or 1 minus cosine squared x times 1 plus cotangent squared x. Thank you. Thank you for noticing.
So both of those are trig identities, no?
Good.
So the first one would be sine squared x. And the other one is, was it cosecant?
Good.
That's right. Yes, it was cosecant. And it's all gonna equal 1.
Yes. But tell me an in-between step.
Oh, wait. So if it's cosecant squared x, can we like split it into a fraction then?
Yes.
Yes. Cosecant, that will be 1 over sine. Well, all in the square. All in the square.
Good.
So that means we can just simplify it by what is it, dividing or subtracting? I think it's you could divide it. You could divide the squared and sines. So you're left with sine. Yeah, sine squared. I think.
We have 2 signs
No,
in the
that
denominator, 2 signs in the numerator. So they're all gone. What's left?
oh, just the one then.
But 1
No.
is what we wanted.
Okay, yeah.
Excellent. Let's do this one and say we forgot that trig identity or just didn't think of it. I just want to practice algebra. And let's see if this is the best. Oh, here's a better one for algebra. So What I was gonna do with this one was multiply it out, like using FOIL. So 1 times 1, 1 times cotangent squared, negative cosine squared times 1, negative cosine squared times cotangent squared. And it's a lovely big mess. And then you end up with 1 anyway. You end up with this. So I want to do something with more algebra in it for y'all. So let's do example 7, where we have sine x over cosine x. We have sine x plus cosine x divided by sine x minus cosine x. And the goal is 1 plus 2 sine x cosine x divided by 1 minus 2 cosine squared x. So we want to start sine x plus cosine x divided by sine x minus cosine x. And the goal is to get to 1 plus 2 sine x cosine x divided by 1 minus 2 cosine squared x. How in the world are we going to start?
Multiply by the denominators. I forget what it's actually called.
Conjugate.
Did you get it right?
Beautiful. So we're going to multiply numerator and denominator by sine x plus cosine x divided by sine x plus cosine x. And let's look at the denominator first. Is this a trig step or an algebra step?
Algebra.
That's an algebra step.
Is it time? What's
It
around?
is. No. It's only like 11:23.
Okay.
Right.
So what do we get in the denominator? If we have a plus b times a minus b, what do we end up with?
All right, what was the question?
If we have a plus b times a minus b, what do we get?
We'll get a squared, and then we'll get a negative ab, and then we'll get positive ba, and then negative b squared.
And what happy thing happens?
What was that?
The happy thing that happens,
Oh, yes.
AB and positive AB go away. So we're not going to do that step every time. We're just going to think a plus b times a minus b is a squared minus b squared. So that's sort of an algebra thing that we're going to really practice on. So in terms of sines and cosines, what is our new denominator?
Sine squared plus cosine squared.
Is it plus?
Minus.
Minus.
Yes, always minus. If you start with a plus in the middle and you multiply by the conjugate, do you get a plus at the end?
No.
Always minus. Good. Okay, and now let's practice squaring a binomial. And I'm just going to write it over here. A plus b squared Somebody tell me.
A squared plus 2ab plus b squared.
Beautiful. It's easy to do the algebra step by step when you've got letters, but when those things that you're squaring are trig functions, this little shortcut helps. Okay, so our A is sine x. So tell me what to write.
So it'd be sine x squared plus 2 sine times cosine
Good.
plus cosine squared.
Excellent. It's always important to take a gander back at the goal after each little step so that you can see what do you already have and what do you still need to fix. So looking at the numerator, what do we already have?
A 2 sine x times cosine x.
Yes. And what do we not have in the numerator?
The 1.
A 1, but we have what instead?
Sine squared and cosine squared.
Yeah. What is sine squared x plus cosine squared x?
1.
Yes. So using a Pythagorean identity, I thought you said you couldn't stay all the whole time, Sir Ralph.
Well, looks like I am.
So that's awesome. Using a Pythagorean identity, we're going to replace sine squared x plus cosine squared x with 1. And we have the goal numerator. What about the denominator? We've got sine squared x minus cosine squared x. And the goal is 1 minus 2 cosine squared x. So what do you think?
Is it one, well, sine x square, no, sine square x, sorry. Do we replace it with 1 minus cosine square x?
Good.
Yeah.
And we still have another negative cosine squared x. So are we there? Numerator matches.
Yep.
We have 1. We have a minus cosine squared x minus cosine squared x. Can we combine these?
Yes.
Okay. Okay, great. Let's go ahead and we have 10 minutes. Do y'all want to try to start something new or wait until next time?
Probably wait till next time for that one.
Yeah.
It's too much of a rush.
It is kind of because we have to get started. And I don't know why, but it always takes a little while to get started. So we've got some time for questions. Anybody?
No questions. Just studying.
I know, ma'am.
Okay. Anybody else? Andrew, are you good?
I'm good for now.
Okay. Mari?
I think pretty much just practice. So
Evelyn? Jordan, how are you? They may not be there.
Good.
So, what about Lynette? How are you doing, Lynette?
I'm good. Just need to practice a bunch of these.
Okay, I'm gonna send out a bunch for y'all to practice. I just don't want you to do it in ACEs. It's ACEs will only let you do one kind of thing per step. It's just very, very tedious, and it'll say you're wrong when you're correct, but you've done something they don't think you should be doing at that step. Just anyway, I will send out some. We'll have a
All right.
Thank you.
welcome.
All right.
Bye bye.
See you
thank you,
guys.
teacher. Bye. Have a nice day, everyone.
Bye.